I thought I had washed this board, and then I just discovered it kind of hiding with its back to me. So I'm going to go over it kind of quickly. It's redundant with a lot of the other stuff, but I like the way it's fairly uncluttered, and I think the pictures came out pretty well. Some exceptions. Okay, we have an LC circuit in this case, and we have voltage V of t equals V max times the cosine of omega t minus some theta naught, and we're not going to worry too much about that, but we do come back to that in this series of videos. Okay, differential equation is going to imply that in that case the current is a function of t, which is equal to some maximum current times the cosine of omega t. And the differential equation to which I refer would be this one. And this one, we've seen this. I went over this in another video, maybe before or after you've seen this. But just very quickly, the differential equation is voltage drop across the resistor L di dt plus voltage drop across the capacitor Q over C equals V max sine of omega t. I is dq dt gives us the second order equation, second derivative of Q with respect to t plus Q over LC equals V max sine omega t over L. Let me make one little change there. Okay, I've replaced a couple of sines omega t with this assumption on the voltage here. And I've got this theta naught here simply because the voltage function is going to be out of phase with the current function, and we don't know by how much. So we're going to let theta naught be some phase angle. Could be plus theta naught, could be minus theta naught. This gives us a characteristic solution of our equation, a combination, linear combination of a sine of omega naught t, cosine omega naught t, b and d being arbitrary constants. And of course, that could be expressed as just an a. Well, we can't use a there. Don't want to use c because of capacitance. Or just go with q max times the cosine of omega naught t plus some phase angle that I'll designate by theta hat. Maybe a little hard to read that, but the q max and the theta hat are arbitrary constants. It can be fit to whatever the conditions of the system might be. Okay, and then we have a particular solution. Started to say particle. A particular solution. This is a linear combination of sine omega t and cosine omega t, where omega is the driving voltage, and we get an a cosine of omega t plus some phi, and I used phi for phase angle, so it's probably not a wise thing to have used it here. I was just doing kind of a quick, just doing kind of a quick synopsis of the differential equation, and I wrote things down a little carelessly, so I think I was using a theta tilde in other videos, so that's what I'm going to use here. And these are not arbitrary. These are not arbitrary constants. They're determined by the nature of the particular solution in conjunction with the values of L and C and V max. Okay. Now, if I of t is I max cosine of omega t, then the voltage across the capacitor, which is L di dt, is easily calculated to be negative L omega I max sine of omega t, and that gives us a picture of a phasor with current vector I of t rotating around the unit circle with angular velocity omega. Okay, so that's what we have here. And right there's your I max cosine of omega t, the projection of this vector, and that's the meaning of the phasor. Okay, we have a voltage being a multiple of the sine of omega t. Now it's a negative multiple of sine omega t. That means that makes its phase 90 degrees with the cosine, but 90 degrees in this direction, as we have seen and will see. So that our projection down here is VL max times the sine of omega t. Okay, VL max being negative L omega I max. Okay, there's our phasor. Now, and we also have the diagram that relates our I function, okay, in yellow, to our voltage function in purple. And we see that the negative sign is 90 degrees out of phase with the cosine. The negative sign hitting 0 before the cosine, hence the angle in this direction, hence VL being here as opposed to I being here. So whatever value I is going to take, VL takes first as we rotate around the reference circle, as we rotate through the phasor diagram. We also have omega naught as 1 over the square root of LC. That would be the angular frequency at resonance in this circuit, addressed more extensively elsewhere. The voltage across the capacitor is Q over C, and if your current is I max cosine omega t, then the charge being related to current by the fact that current is a derivative of the charge is integral to the current. It's going to be 1 over omega t, C times your I max sine of omega t. And very simple. And this is a positive sign, which it turns out precedes the current. It's 90 degrees out of phase the other direction. I mean, it follows the current, I'm sorry. 90 degrees out of phase in the other direction from the VL. And we'll see that in subsequent diagrams, or depending on when this video is viewed, you can see it at various points.